Hello everyone, my name is Pornvimol Kongkiatkai, and in this video, I would like to talk about the valence bond and molecular orbital theories. I would like to break the content into 5 different topics, starting from demonstrating the difference of valence bond and molecular orbital theories. After that, it will be the topic of valence bond theory of hydrogen gases. Next, the valence bond theory of water and methane, then the valence bond theories of main group elements, and finally about the valence bond theory of transition metals. The first topic is the difference of valence bond and molecular orbital theories. Both MO and VB are used to describe the chemical bonding in molecules. Valence bond theories assume that all bonds are localized bonds formed between two atoms by the donation of an electron from each atom, while the molecular orbital are not localized on single atom but extend over the entire molecules. The structures shown are representing the hydrogen of both theories. On the left, X representing the electron on HA, and the red dot represents the electron of HB, while the structure on the right, which is the structure of H2 from molecular orbital theories, it doesn't show that the electron belongs to HA or HB, but belongs to the whole molecule. So they say that VB is about localization while MO is about delocalizations. Then we'll move on to the valence bond theory of hydrogen gas. As shown on the previous slide, that each electron belongs to the different hydrogen atom. The structure drawn can be swapped as shown in this structure. The hydrogen gas molecules doesn't only have the covalent structure, but they also have the ionic structures. The covalent structure is 94% and the ionic structure is 6%. So in total, that there are 4 forms of hydrogen gas molecules. Then we would like to focus on the valence bond theory of water and methane. Water, which is H2O. The electron configuration of oxygen is 1s2, 2s2, 2p4. The electron configuration can be written into different energy level diagrams, as shown. The structure of water is also shown on the slide with 104.5 degree angle. The wave function of hybridization is 1 over n, which n representing the normalization, times 2p plus gamma 2s. Cos theta equal to the negative gamma square. The percent of s character is gamma square over 1 plus gamma square. And the percentage of b character is 1 over 1 plus gamma square. The structure of methane is shown on the slide. Methane CH4 has the hybridization of sp3, meaning that there are S for 25% and P for 75%. In order to prove the hybridization, we sub in the angle of 109.5 to the equation of cos. So it is equal to negative 0.33, and the percentage of S and P as shown below. It can be concluded that S over P is equal to 1 over 3. The table is used to represent the percent character of different hybridizations, showing the percentage of S character and also the percentage of P character. The hybridization of SP, the molecule should have the angle of 180 degree. So the percentage of S character is equal to 50, which is equal to the percentage of P character. And the hybridization of sp2, the molecule should have the angle of 120 degree. So the percentage of S is equal to 33%, and the percent of P character is 66%. And finally, the hybridization of sp3, the molecule should have the angle of 109.5, So the percentage of S character is equal to 25, and the percentage of P character is equal to 75. And for the water molecules, H2O, the water molecule should have the angle of 104.5. So it is cos 104.5 degree, which is equal to negative 0.25. And the percent of S character is 0.25 over 1.25. And the percent of P character is 1 over 1.25. So the S over P is equal to 1 over 4. And the hybridization of bonding electron of water is concluded to be sp4. And the gross hybridization of water is sp3. Then we move on to the valence bond theory of main group elements. There are two different structures of H3. First is H3 plus containing 2 electrons, and the second is H3 minus containing 4 electrons. And H3 plus is 3-centered 2-electron bond or hypovalent, and H3 minus is 3-centered 4 electrons bond or hypervalent. The example of hypervalent is B2H6. Normally, the structure of B2H6 is shown on the top with 12 electrons. But to demonstrate this molecule with 3-centered 2-electron bond, it should be drawn as the structure below. PCl5 is the example of hypervalence, or 3-centered 4-electron bond. To show the structure of PCl5 with 3-centered 4-electron bond, the structure should be drawn as the structure on the right. There is one 3-centered 4-electron bond presenting in the red box. For borane, chlorso is used to represent the BnHn plus 2, and the example of chlorso is octahedral B6H6 with the charge of 2 minus, and nido is BnHn plus 4. The example of nido is B2H6, and finally is the arachno with BnHn plus 6 formula. The example of arachno is B4H10. STYX is used to find the structure of borane. S is number of 3-centered 2-electron bond BHB, and T is number of 3-centered 2-electron bond BBB, and Y is the number of bonding BB, and finally X is number of group of BH2. And the equation BPH plus Q, number of H atom is equal to S plus X, which is equal to Q, and number of B atom is S plus T, which is equal to P. And finally is the valence bond theory of the transition metals. PTH4 2 minus is the representation of the valence bond theory of transition metals. Platinum 2 is D8, and for hydrogen has 4 electrons. So in total there are 16 electrons, which are over 12 electrons in the shell. So the structure should be adapted to represent the molecule with 12 electrons in the bonding. Thank you for listening to my video, and I hope this video would help you to a better understanding about the valence bond and molecular orbital theories. Don't forget to also like this video. Thank you.